Mercury, the smallest planet in our solar system, was previously regarded as a barren, desiccated world, subjected to relentless solar radiation. It is, however, worth noting that this seemingly unremarkable planet is, in fact, concealing some of the universe's most astonishing secrets. That it may be far more complex, enigmatic, and dynamic than previously assumed? For decades, Mercury has remained relatively unstudied in the context of planetary exploration. While Mars, Venus, and the distant icy moons of Jupiter have collectively captured the attention of the scientific community, Mercury has remained relatively unstudied, situated at the closest point to the Sun, and exhibiting conditions that have been perceived as extreme and uninteresting. However, recent data obtained by the James Webb Space Telescope is prompting a re-evaluation of our previous assumptions regarding this diminutive planet. The latest findings from NASA have prompted scientists to rethink their understanding of Mercury, with the potential to alter our knowledge of planetary formation and evolution. What makes this discovery so significant? This article will examine the evidence from past missions and the latest findings, exploring the implications for our understanding of Mercury. For centuries, Mercury was regarded as a relatively inactive planet, exhibiting minimal geological or atmospheric activity. The planet's surface temperatures can reach 800 degrees Fahrenheit during the day, only to plunge to negative 300 degrees Fahrenheit at night. In such an environment, the possibility of sustaining life as we know it was deemed implausible. The prevailing view was that geological processes had ceased to operate, having become fixed in a state of stasis. However, this assertion is demonstrably false. One of the most unexpected findings was the realization that Mercury is not merely a fixed mass of rock. A substantial and concentrated core, considerably larger than previously estimated, is situated beneath the surface. This core, which accounts for more than 85% of Mercury's volume, is thought to be one of the most important factors in explaining many of the planet's unusual characteristics. Indeed, scientists now posit that Mercury's peculiar core may be the consequence of a cataclysmic event, a violent collision in the planet's early history, resulting in the removal of a significant portion of its outer layers. The hypothesis that Mercury was formerly a significantly larger planet, potentially twice its current size, before losing its outer shell in a cataclysmic impact, represents one of the most compelling theories to emerge in recent years. It is therefore plausible to hypothesize that the evolution of Mercury was significantly influenced by a hit-and-run event occurring amidst the turbulence of the nascent solar system. Such an occurrence would also help to elucidate why this relatively small planet has a core that is so disproportionately large in comparison to its mantle and crust. The evidence pointing to this event has opened up new avenues of investigation as scientists endeavor to comprehend the true events that transpired billions of years ago. However, the composition of the core is not the only aspect of the planet that remains a mystery. The surface of Mercury itself is replete with enigmas. In 1974, NASA's Mariner 10 spacecraft provided our first close-up observation of Mercury, revealing a surface with a cratered topography similar to that of the Moon. Upon initial observation, this appeared to corroborate the hypothesis that Mercury was a geologically inactive world. However, as more data became available, the situation became much more complex. One of the most unexpected findings from Mariner 10 was the discovery of a magnetic field around Mercury, which was surprising given the planet's relatively small size. The generation of magnetic fields is typically associated with the movement of molten metal in a planet's core. However, the lack of geological activity on Mercury, coupled with its relatively small size, left scientists perplexed. The question then arose as to how this tiny planet could sustain a magnetic field. 3 decades later, NASA's Messenger mission yielded further insights, yet simultaneously posed new questions. Messenger not only validated the existence of Mercury's magnetic field, but also illuminated its distinctive characteristics. In contrast to Earth's magnetic field, which exhibits a relatively symmetrical structure, Mercury's magnetic field displays a peculiar asymmetry, exhibiting a markedly stronger presence in the northern hemisphere than in the southern hemisphere. What could be the underlying cause of such an imbalance? The answer lies deep inside the planet. Messenger's data suggested that Mercury's core is still partially molten, unlike the solidified cores of many other small planets and moons. This molten core could be generating the magnetic field, but the irregularity of the field suggests that there's something highly unusual about the way Mercury's core is behaving. Could it be that Mercury's core is cooling and solidifying at different rates, leading to this strange magnetic phenomenon? Or is something else at play, something we don't yet fully understand? In addition to the planet's substantial core and unconventional magnetic field, observations have revealed indications of volcanic activity on Mercury, a discovery that has profoundly impacted the field of planetary science. For an extended period, it was assumed that the volcanic activity on Mercury had ceased long ago. However, the instruments on board Messenger identified regions of the surface that had been altered by explosive volcanic activity, indicating that Mercury may still exhibit geologic activity. Moreover, these explosive eruptions were not of a minor magnitude. The data obtained by Messenger revealed the existence of vast plains of smooth lava, some of which are believed to be as recent as 1 billion years old. This is a relatively young age in geological terms. This indicates that Mercury may have exhibited volcanic activity at a much more recent period than was previously anticipated. The notion that volcanic activity could have persisted on a planet situated in such close proximity to the Sun, where conditions are sufficiently harsh to vaporize metal, challenges numerous assumptions regarding planetary geology. However, the volcanic activity observed on Mercury gives rise to further inquiries. How did such explosive events originate? And what implications do these findings have for the geologic past and future of Mercury? Perhaps the most striking discovery, however, was not made by Messenger, but rather by earlier radar observations, and subsequently validated by NASA probes: the presence of water ice. Indeed, the presence of water ice on Mercury, the planet closest to the Sun, has been confirmed. How could this be possible in such an inhospitable, sun-scorched environment? It has been determined that there are regions of permanently shadowed craters in close proximity to Mercury's poles, where the sun's rays are unable to penetrate. In these craters, which are perpetually shrouded in darkness, temperatures can reach as low as -300 degrees Fahrenheit, a temperature sufficient to preserve ice for billions of years. This discovery has fundamentally altered our understanding of the planet. The discovery of water ice on Mercury suggests the possibility that the planet may have captured water from comets or asteroids over the course of its history, a process that may still be occurring. The discovery of water ice on Mercury, however, raises more than just a scientific curiosity. It also prompts a number of intriguing questions about the planet's potential to harbor life. Could these icy craters, shielded from the sun's heat, serve as refuges for microbial life? Could Mercury have once had conditions that were more hospitable, allowing life to take root in these protected areas? Although the answers have yet to be determined, the discovery of water on Mercury represents a significant development. It prompts a reevaluation of not only the planet's history, but also its potential as a future exploration target. With the forthcoming BepiColombo mission scheduled to arrive at Mercury in 2025, further insights into this enigmatic world's hidden treasures may be imminent. In addition to the already remarkable characteristics of Mercury's surface, core, and magnetic field, the planet also exhibits one of the most anomalous orbital patterns observed in the solar system. Mercury's day is longer than its year, with a period of 176 Earth days for a single rotation and a period of 88 days for a single orbit around the Sun. This distinctive spin-orbit resonance gives rise to a peculiar day-night cycle, whereby an observer on Mercury would witness the Sun's apparent movement across the sky, followed by a cessation of movement, a reversal of direction, and then a resumption of forward motion. One can only imagine the difficulties of attempting to determine the time on Mercury. This peculiar behavior is due to the gravitational influence of the Sun, which has locked Mercury into this rhythm over billions of years. The planet's proximity to the Sun results in extreme temperature swings, with temperatures reaching levels that would melt lead during the day and freezing nitrogen at night. The surface of Mercury is also shaped by forces that originate beyond its own core. In the vicinity of the planet's southern pole, an area designated as the chaotic terrain is observed. This region is distinguished by the presence of ridges, valleys, and hills, which appear to have been shaped by intense seismic activity and volcanic activity. This chaotic landscape is likely the result of the sun's immense gravitational pull, which exerts such powerful tidal forces on the planet that it literally shakes Mercury's surface. Over time, this gravitational tug-of-war has caused significant changes in the planet's orbit and rotation, resulting in a landscape that appears to have been subjected to persistent and extensive disruption. These seismic events may also be linked to Mercury's gradual cooling process. As the planet's core continues to solidify, its crust is undergoing contraction, resulting in the formation of thrust faults on the surface. These cracks serve as indicators of the planet's shrinking as its core cools. The significance of Mercury extends beyond its designation as the smallest planet in our solar system. It may, in fact, contain vital information that can help us comprehend the early history of the solar system. The prevailing scientific opinion is that the current form of Mercury may be the result of a violent and chaotic era that occurred billions of years ago. During this period, young planets and massive space objects collided at high speeds, resulting in significant alterations to their ultimate fate. One of the most prominent hypotheses is that Mercury was formerly a considerably larger planet, potentially rivaling Earth in size. In this scenario, Mercury would have lost the majority of its outer layers in a cataclysmic impact with another large object, leaving behind only its dense, metal-rich core. This theory provides an explanation for why Mercury's core is so disproportionate, comprising nearly 85% of the planet's volume, which is an anomaly compared to other planets in our solar system, which typically have much thicker mantles and crust. If this hypothesis is indeed valid, it gives rise to significant inquiries pertaining to the formation and evolution of planetary bodies. Was Mercury the result of an interplanetary collision on a massive scale? Moreover, if this hypothesis is indeed correct, it raises the question of whether similar events may have shaped the formation of other planets, including Earth. The hypothesis that a young solar system was once a violent place, where planets were torn apart and rebuilt through a series of collisions, is gaining traction among scientists. An understanding of the unique characteristics of Mercury may facilitate the unlocking of the secrets of those ancient, chaotic days. This hypothesis has significant implications not only for Mercury, but also for our understanding of the broader process of planetary formation. If planets like Mercury can lose such large portions of their mass, it is plausible that many other planets may have undergone similar transformations in the distant past. This new perspective could even inform the search for exoplanets, enabling us to refine our expectations regarding the characteristics of other star systems. Another conundrum that scientists have been attempting to resolve pertains to the surface chemistry of Mercury. Unexpectedly, Messenger observed the presence of considerable quantities of volatile elements, including potassium, sodium, and sulfur on Mercury. These are typically gases that exist in a vaporous state at elevated temperatures. Given that Mercury is situated in close proximity to the Sun and experiences extreme heat, this observation is perplexing. It is unclear how these elements could have survived in Mercury's intense environment without being either burned off or vaporized. One potential explanation is that these elements were delivered to Mercury by comets or asteroids long after the planet's formation. It is possible that these impacts delivered volatile compounds that were subsequently trapped within the surface of Mercury, protected from the sun's heat by the planet's distinctive geography. If this hypothesis is substantiated, it would indicate that the geological evolution of Mercury has been influenced not only by its proximity to the Sun, but also by interactions with objects from distant regions of the solar system. This also indicates that volatile elements can be found on planets that were previously assumed to be too hot to retain them, which opens up new possibilities for planetary science. The presence of these volatile elements adds another layer of complexity to Mercury's geological history. How did these elements become so abundant on the surface? And what can we infer about the planet's interaction with its surroundings based on this? These are questions that the upcoming BepiColombo mission will help answer. Another area of scientific interest regarding Mercury is its exosphere, a tenuous, almost ethereal layer of particles that surrounds the planet. In contrast to a genuine atmosphere, the exosphere of Mercury lacks the requisite thickness to impede heat flow or sustain atmospheric circulation. Instead, it is a perpetually evolving blend of particles comprising oxygen, sodium, hydrogen, and even water vapor, all of which are continuously escaping into the cosmos. The exosphere is predominantly shaped by the solar wind, a stream of high-energy particles emanating from the sun at remarkable speeds. Due to Mercury's proximity to the sun, the solar wind exerts a considerable impact on the planet's surface, with a level of intensity that is unparalleled in the solar system. The solar winds pick up particles from the surface of Mercury, propelling them into the exosphere and subsequently into space. One of the more recent discoveries made by Messenger was the surprising amount of water vapor in Mercury's exosphere. This finding was completely unexpected and has prompted scientists to consider the potential sources of this water vapor. One hypothesis is that it may be released from deep within the planet, potentially as a result of ongoing geological activity. Alternatively, it could be delivered by comets, which are known to carry water ice in their tails. An understanding of the interaction between Mercury's exosphere and the solar wind is of paramount importance for the comprehension of the planet itself, as well as for the elucidation of the impact of the solar wind on other planetary bodies. Furthermore, insights may be gained into the evolution of atmospheres and exospheres in diverse environments, which will prove invaluable for the study of exoplanets and other celestial objects. The magnetic field of Mercury, though considerably weaker than that of the Earth, continues to hold the attention of researchers. As has been established, the magnetic field of Mercury is markedly asymmetrical, exhibiting a greater strength in the northern hemisphere than in the southern. This irregularity has posed a significant challenge to scientists since its discovery, as it indicates the occurrence of distinctive processes at the core of Mercury. In most cases, magnetic fields are generated by the movement of molten metal within a planet's core, as is the case with Earth. However, the cooling and solidification of Mercury's core are occurring at disparate rates, which may be a contributing factor to its anomalous magnetic behavior. The gradual solidification of Mercury's core is responsible for the planet's shrinkage, which in turn gives rise to the formation of fault scarps, or giant cliffs, on the surface as a result of crustal buckling under the pressure. However, there is more to this story. Mercury's spin-orbit resonance, wherein the planet rotates 3 times for every 2 orbits around the Sun, may also play a critical role in the formation and evolution of its magnetic field. The manner in which Mercury rotates and orbits the Sun could be influencing the movement of the liquid metal in its core, which in turn affects the strength and orientation of the magnetic field. This has led scientists to rethink the processes by which planetary magnetic fields form and evolve, not just on Mercury, but on other planets as well. An understanding of Mercury's magnetic field may assist in the resolution of some of the enigmas surrounding magnetic fields on other planets, including Mars and Venus. Furthermore, it may provide insights into the conditions necessary for planetary habitability. A robust magnetic field is vital for the protection of a planet's surface from the harmful effects of solar radiation, which could be a determining factor in a planet's potential for habitability. One of the most intriguing, albeit speculative, questions raised by recent discoveries on Mercury is whether life could potentially exist in its most extreme environments. Although the surface of Mercury is inhospitable, with temperatures reaching 930 degrees Celsius on one side and negative 183 degrees Celsius on the other, the discovery of water ice in permanently shadowed craters near the poles presents intriguing possibilities for the existence of life. On Earth, extremophiles, microorganisms that are capable of thriving in environments that are among the most extreme on the planet, have been demonstrated to survive in conditions that were previously believed to be incompatible with life. It is therefore pertinent to inquire whether analogous life forms might exist within the dark, icy craters of Mercury. These craters, protected from the sun's unrelenting heat, offer a haven of stability in an otherwise tumultuous environment. Although the possibility of life on Mercury remains purely speculative, the discovery of water ice and organic materials raises intriguing questions about the planet's potential to have harbored life in its distant past, or perhaps even today. Exploring this possibility is one of the reasons why future missions to Mercury, like BepiColombo, are of great importance. By studying these icy craters in greater detail, scientists aim to gain a deeper understanding of the conditions that exist there and whether they might support microbial life. Even if life is not discovered, the insights gained from Mercury could prove invaluable in guiding the search for life on other planets, particularly those in extreme environments. In the forthcoming years, the BepiColombo mission, scheduled for launch in 2025, will represent a significant advancement in our comprehension of Mercury. A collaborative endeavor between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, BepiColombo is designed to provide unparalleled insights into Mercury's surface, magnetic field, exosphere, and interior structure. BepiColombo is equipped with a comprehensive array of sophisticated instruments, which will enable it to orbit Mercury for an extended period, facilitating the acquisition of meticulous data that will facilitate the resolution of numerous queries posed by preceding missions. What is the true nature of Mercury's core? The mission will address a number of fundamental questions regarding the evolution of Mercury, including the nature of the planet's interior, the origin of its polar craters, and the potential for the existence of extraterrestrial life. Additionally, the mission will yield insights into the formation and evolution of planetary bodies, which will contribute to our understanding of the processes that shape the solar system.